Chapter 29, Magnetic Fields. So far we've focused our attention only on the electric field. Electric charges produce an electric field, and then we studied what happens when electric charges are in motion, forming a current powered by a battery. So, what about the other side of E&M, the so-called magnetic fields? And why do we put our first chapter of magnetic field right after we studied electrical current? Well, historically, the magnetic phenomena were known to people for many years, for many centuries, as a matter of fact, even though the discovery of the connection between electricity and magnetism were relatively recent, just about 200 years ago. We have all heard and in fact actually used magnetic stones, right? You know, with every piece of magnetic stone, there comes two poles, which we call north and south. We might as well call them plus or minus if we wanted to, but for historical reasons we call them north and south because they play a role in determining directions on the surface of the earth. So we call them north and south. And just like charges, these two different types of poles behave differently. Like poles repel, unlike poles attract, just like charges repel, unlike charges attract. So in this case, in this sense, it's kind of similar to the behavior of electric fields. But it is something, there is something very different between electrical case and magnetic case, in a sense that in the electrical case, it is possible to separate positive and negative charges. On the other hand, in a magnetic case, it is impossible to separate the north pole from the south pole. If you cut the stone in half, what are you going to get? You're only going to get two smaller magnets, each with its own set of poles. It's like this. You automatically would generate a south pole and a north pole. And you can keep on doing it. No matter what you do, you find that we are not able to separate the north pole and the south pole. Okay, it is for this reason that we call these poles instead of charges. Otherwise, we would have called them magnetic charges. But a pole naturally comes with two ends. So that is why we call them poles. As a matter of fact, if we are able to separate one pole, one magnetic pole from the other, we will get something which we call magnetic monopoles. Okay, magnetic monopoles, we speculate it should exist under the right circumstances. Many physicists believe they should, but we have not found one yet. So, that's some similarities and differences between electric and magnetic phenomena. One of the things about magnetic fields is that it is related to navigation. Okay, we've all used compasses. A compass can point in a north-south direction, and it is because a compass basically is just a small magnetic needle, small magnetic stone mounted on a free axle at the center, so that it is free to turn under the influence of the Earth's magnetic field. And the reason why it can indicate north and south direction is because the Earth itself is just a giant magnet. Okay, so therefore it will exert a force, or more precisely a torque, on the compass, which is just a magnetic stone, causing it to align with north-south direction. And it is for this reason that we call the poles, north and south poles, the magnetic poles of a magnetic stone. We don't call them plus or minus for this reason. As a matter of fact, if you have a compass, okay, and you let it turn freely, put it horizontally, let it turn freely, then the north pole of this compass, which is this side, will point toward the geographical north. Okay, so if you go there, point this way, you will be pointing towards the north pole of the Earth, the geographical north pole of the Earth. And that is where Santa lives, okay? And the south pole of this compass will point towards Antarctica. Okay, it is for this reason we call this particular magnetic pole on the compass the north pole. In fact, it means it's the north-seeking pole. And again, this is because the Earth has its own magnetic field, and since disk-like poles attract, if the north pole of the compass points towards the geographical north, tell me, near the geographical north of the Earth, okay, which is the Arctic region, would you find the north or the south pole of the magnetic fields of the Earth? In other words, is the geographical north of the Earth its magnetic north pole or its magnetic south pole? Well, you see, since dislike poles can only dislike poles attract, right? You can imagine it is actually the magnetic south of the Earth that's attracting the magnetic north of this compass. So the magnetic south of the Earth is in fact in the same general region as the geographical north of the Earth. Make sense? Okay, so this is how a compass would work. Now, we had these knowledges long before we realized there was a connection. There was a connection between electricity and magnetism. And the discovery of the connection between electricity and magnetism came in fact as an accident. Okay, it was an accidental discovery. We attribute it today to Hans Christian Ørsted, who was a Danish scientist. And he made that discovery accidentally when he was preparing a lecture demonstrating electric current in the year 1819. Okay, so it's less than 200 years ago. And how did he make that discovery? Well, he was preparing for a lecture demo of an electrical current, which is powered by a battery. So when you flip on a switch, a current starts to flow. Okay, and in doing so, he just happened by accident to have a compass nearby. You know, to have a magnetic compass nearby. And the funny thing is, as soon as he turned on the switch to form a current, the compass starts to turn. Okay, of course that caught his attention. You know, many scientific discoveries were by accident, but it takes a person with a trained eye, okay, with a lot of curiosity and trained eye, to follow up on that and actually discover what's behind those accidents. So he made some systematic study of what's going on. For example, when you reverse the current, he found the compass will turn the other way, and so on. Now we know the compass is subject to a magnetic force. Okay, so it has magnetic behavior, and now it turns out an electrical current, in other words, electrical charges in motion, can also exert a force on a compass. So what is your conclusion? The conclusion is that an electrical charge in motion, in other words, a current, electrical current, can cause a magnetic field. Okay, the magnetic field of that current will interact with the magnetic field of the compass, therefore causing the compass to turn. So that is the first concrete evidence that electricity and magnetism go hand in hand. And here is, therefore, our conclusion. It says electrical current, sometimes we just call it current, exerts a force on a magnet. This is from our discovery. And that necessarily means an electrical current must produce a B field. B field means magnetic field, just like E field means electric field. Okay? Because by producing a B field of its own, the electrical current will interact with the B field produced by the compass, and these two B fields interact with each other, will cause a force between the compass and the charge-carrying current. Okay. Now, it also means that a magnetic field, a B field, must exert a force on a moving charge. Because a moving charge, which is equivalent to a current, can produce a magnetic field, right? We learned that. And then, therefore, another external magnetic field can then interact with it and exert a force on it. Okay, so these are the conclusions we can draw from this demonstration. Now, so one of the things that we did not really discover the connection between electricity and magnetism earlier probably was because if you put a stationary charge, expose it to a magnetic field, for example, put it near a compass or near a ball magnet, nothing is going to happen. Okay, it is not just an electric charge that you need. That charge has to be moving, has to form a current, has to be moving, and that is when you activate its magnetic field. If it's stationary, you only have an electric field. Okay, if the charge is moving, it will produce both an electric and a magnetic field. So, conversely, a magnetic field can only exert a force on a charge when it is moving. Okay, it won't do anything when it's stationary. Now, so we have a magnetic force that we have to investigate. A magnetic force exerted on a moving charge. We're going to start with a single moving charge, and then we're going to extend our discussion to the case of of electrical current, which is basically just made by a whole bunch of moving charges. Now, suppose for the sake of discussion for now, that the velocity of that moving charge q is not parallel or anti-parallel. In other words, it is not collinear with the magnetic field B. Okay, and if that is the case, then we will be able to uniquely form a plane which is defined by these two vectors v and b, right? And you know the magnetic force exerted by the field B on this moving charge q, moving with a velocity v, should depend on both q and v, in addition to the magnetic field itself. Now q is a scalar, but both b and v are vectors. So in other words, whatever magnetic field you'll be getting, that field, whatever magnetic force this guy will experience, that force, which is a vector, will be determined by two other vectors, v and b. Okay? My first question is, what should be the direction of that resulting magnetic force? Here, I draw a line that is perpendicular to the plane, which means it's perpendicular to both these two vectors, v and b. Okay, I want to argue based on symmetry arguments. I don't just want to say it's experimental fact. Of course, you can always say that, but I can actually argue based on symmetry that the magnetic force exerted on this moving charge by this magnetic field just has to be perpendicular to both v and b. In other words, it has to be along that line. Okay, it has to be along that line. That is perpendicular to the plane defined by b and v. It has to be. How do we know that? Well, we use symmetry argument. That is what we do. Suppose the force that you get is not perpendicular to b and v. In other words, it's not along this axis. Then it's somewhere here, let's say. Okay, somewhere here, pointing in that direction. Okay, f of b, or f. I want to show that something would be wrong if that happens. How do I know that? Well, here's the thing. You know f is a function of v and b. And what if I reverse the velocity? In other words, the charge moves oppositely. Okay, a charge going in the opposite direction is like having a reverse current, right? Having a reverse current, of course, that would necessarily mean that the magnetic force exerted on it would be reversed. Okay, that makes sense? So if I reverse v to the opposite direction, so v now points in the opposite direction, okay, the force will have to be reversed. So the force would have to point that way, right? Oppositely. On the other hand, we know the force is caused by the magnetic field. What if the magnetic field itself reverses? Okay, so the magnetic field goes that way. Okay. So the magnetic field is also reversed. So I would now have a negative v and a negative v. If you reverse the magnetic field, keeping everything else the same, then of course you know the resulting magnetic force will also be reversed, right? So you reverse either one of them, you find b, that force goes to negative force. But what if you reverse both of them simultaneously? Now what? If you reverse both of them simultaneously, then the force will be reversed twice, going this way and going back, right? So what happened to the force? Nothing. Okay. As a result of reversing both b and v, the force should be the same, to retain the same direction. It should be the same force. However, here's where the symmetry argument comes in. Okay, suppose you take the original two vectors, v and b, and you turn both of them rigidly about this axis by 180 degrees. Can we do that? Okay, if I did that, then this b actually becomes negative b, this v becomes negative v. We know that as a result, the force, the magnetic force exerted on a charge should not change, as we just argued, right? Yet on the other hand, if the force pointed that way, as I rotate these two guys, look at these three vectors, v, b, and f. If I rotate about this axis, all three should turn through the same angle, right? They should turn through the same angle. So as b becomes this one, v becomes that one, what happened to f? F should also turn 180 degrees to here. See that? To here. But these two angles are the same. Okay, just you know, it will be just turned by 180 degrees. But wait a second, we know f should not change, right? By symmetry argument, we know f should not change because we reverse both b and v. And that means these two f's really should be the same vector. How is that possible? That is only possible if this angle and that angle are both equal to 0, right? then no matter what you do, how turn by 180 degrees, nothing should happen. And that means the only possible direction for F would be along that line. Okay, see that? Which is perpendicular to both V and B. Well, as a matter of fact, it can also point backwards. And as long as it's along that line, you'll be fine. But that is the only possible line in which the magnetic force can exist. Okay, so from symmetry argument, we learned that F has to be perpendicular to both of these vectors, B and V. Now, in particular, what if B and V are parallel to each other? Well, we'll see that case in just a minute. Okay, in just a minute. But we have here a vector, F, determined by two other vectors, V and B. And it is perpendicular to both of them. Okay, what does that remind us mathematically? Have we learned a case before, mathematically, that when a vector is determined by two other vectors and the resultant vector is perpendicular to the first two vectors? Well, if you recall, we defined something like that. We call it what? Vector product or cross product, right? So C is defined as A cross B, generally. These are just general vectors. C is perpendicular to both A and B. And what is the magnitude of C? It's defined as A B sine theta. Right? Now in our case, we have a magnetic force that is perpendicular to both of these vectors, B and V. Okay, B and V. And it's determined by two vectors, B and V. So is it possible that our magnetic force, in fact, can be written as the cross product or vector product of these two vectors, V and B? Well, if you do an experiment to find the magnitude, okay, to find the magnitude of the magnetic force, then you'll find, yes, in fact, this is true, okay? In fact, the magnetic force, we already know it's perpendicular to both V and B, but as far as the magnitude is concerned, it turns out to be equal to the magnitude of V times the magnitude of B times sine of the angle between them. It is proportional to sine theta, not cosine or any other angle. So the cross product becomes very handy one more time. We can use it to express the magnetic force. To express the magnetic force. Here is the expression, therefore. For the magnetic force exerted by a magnetic field B on a moving charge Q, moving with velocity V. Okay, again, we argued that F has to be perpendicular to both V and B, but we did not uniquely fit that direction because it either point this way or that way. Okay, so which way does it point at? Well, that is by convention, okay? Because the way we uniquely pick up one of these is by defining a possible, the positive direction of the magnetic field, okay? So that is by convention. We pick up one of these two, such that by our convention of magnetic field, it is always V cross B, not B cross V. Okay, if it's V cross B, it's upward. If it's B cross V, it will point downwards. So that part is by convention. Okay, with that, you find that the magnitude is QVB sine theta as usual. We can say something about this new quantity, magnetic field. We haven't studied how to calculate, how to produce the magnetic field. We know it can be produced by current, electrical current. We have not learned how to calculate the magnetic field produced by current. As a matter of fact, we're going to do things reversely, okay, with these two chapters, 29 and 30. In this chapter 29, we're going to first assume there is a magnetic field, the strength of the field is B, and given that B field, let us figure out what can it do. Okay, it can exert a force on a moving charge, on a current, that sort of thing. We can study all of these, the behavior of the magnetic field. And only in the next chapter, chapter 30, we're going to study the origin of the magnetic field. That is, how one might calculate the B field produced by an electrical current. Okay, so that is the order. We're not going to study how to calculate B until the next chapter, assuming there is a B. Now, this still is a new physical quantity, so we can introduce a new unit for it. Okay, this is the SI unit of magnetic field. It is defined, once again, with the name of a scientist. This particular one, very famous American physicist and engineer by the name of Tesla, Nikola Tesla. Okay, and you probably have heard these things such as the Tesla machine. Okay, and it is abbreviated capital T, what is Tesla equivalent to? We use this formula. Okay, see, use this formula to figure that out. It will be Newton right here, divided by what? Q times V. Q is charge, and V is meters per second. Okay, now, Coulomb per second, that is amp. So it's Newton per meter per amp. So 1 Tesla is equivalent to 1 Newton per meter per amp. That is the SI unit of the magnetic field. Is this a large unit or a small unit? You know volt is a small unit, right? 1 volt is nothing, right? 1 farad is a large unit. Okay, 1 farad is a gigantic capacitor. What about 1 Tesla? Well, it turns out 1 Tesla is also a rather large unit, okay? I mean, it's not as large as something like 1 farad, which is almost unheard of. But 1 Tesla is still quite a large magnetic field. In the next chapter, when we study how to create a magnetic field, I will show you what kind of trouble people will go through in order to create just a 1 Tesla field. Okay, it is not easy, even though it can be done. It's quite a big machine, you know, that will produce 1 Tesla. So Tesla is a rather large unit, and because of that, we use also a smaller unit to augment it, and that smaller unit you may have heard about. It's called Gauss. Okay, it's named after Gauss, of course, the same Gauss under Gauss's law. So GS. Okay, or G sometimes called. 1 Gauss is 1/10,000th of a Tesla. Okay, 1/10,000th of a Tesla, and this is a unit we also frequently use because Tesla is often too big. All right, going back to the same problem that we asked before. When V is parallel to B, what should the value of F be? Well, you say no problem from this formula. When sin theta equals 0, right? Sin theta equals 0 because V and B are parallel to each other. Then shouldn't F be 0? Of course, the answer is right. F is definitely 0. But the thing is there a way we can figure this result out without even using this formula? Do we know there exists an intrinsic reason why when B and V are parallel to each other, F has to be 0? Actually, anti-parallel would do too. Okay, well, think about it. We know that F has to be perpendicular to both of them, right? B and V. But if V and B are parallel to each other or anti-parallel, then they actually exist on the same line, right? Now, if they exist on the same line, then tell me, can you uniquely form a line? Can you uniquely form a plane which contains these two vectors? No, you can only do so when these two vectors are not parallel to each other, right? If the angle between them is 0, you cannot uniquely define a plane that is parallel to both vectors. That plane can be any direction. And what we want to know, we know for sure that F is perpendicular to both B and V, but B and V are not in the same direction, okay, along the same line, or anti-parallel, along the same line. And then that means that F can be in anywhere on a plane that is perpendicular to this line. So F can point this way, can point this way, can point this way, can be any direction. Now, how can you have a vector with an arbitrary direction? We know F is unique. You cannot have an arbitrary value for the direction of F. And when that happens, the only argument we can make is that F has to be 0. Okay, it does not exist. That's why we know that B and V have to be cannot be collinear. Otherwise, the magnetic force has to be 0. All right. So this formula is of pivotal importance in this chapter. It tells us how to find the magnetic force on a single moving charge. We'll come back to that formula to see what kind of wonderful applications we can get out of it.